Chapter 12, Matter. This lecture will help you understand the properties of matter, how to describe the properties of solids, Hooke's law, and how to calculate the amount of stress on objects. The three most common states of matter are gases, liquids, and solids. Gases are compressible fluids. Their molecules are widely separated. Liquids are relatively incompressible fluids. Their molecules are more tightly packed. Solids are nearly incompressible and rigid. Their molecules or ions are in close contact and do not move. Solids have a definite shape that is not easy to change. Properties of solids we will discuss are cohesion, adhesion, tensile strength, hardness, ductility, malleability, and elasticity. Cohesion is the force of attraction between like molecules. The cohesion forces hold the closely packed molecules of a solid together and keep its shape and volume from being easily changed. Cohesion can also be shown by grinding and polishing the surfaces of two like solids and then sliding their surfaces together. For example, take two pieces of polished plate glass and slide them together. Try to pull them apart. The force of attraction of the like molecules of the two pieces of glass makes it difficult to pull them apart. Adhesion is the force of attraction between different or unlike molecules. Common examples include glue and wood, adhesive tape and skin, and tar and shoe soles. Tensile strength is the measure of the resistance to being pulled apart. It is the measure of the cohesive forces between adjacent molecules. It is the ratio of the force required to break a rod or wire divided by the cross-sectional area of the rod or wire. The tensile strength of a rod or wire is found by putting it in a machine that pulls the rod or wire until it breaks. The hardness of a solid is a measure of the internal resistance of its molecules to being forced further apart or closer together. More commonly, we classify the hardness of a solid in terms of its difficulty in being scratched using a scratch test. The given material is scratched in a certain way. Its scratch is then compared with a series of standard scratches of materials that form an arbitrary hardness scale from very soft solids to the hardest known substance, diamond. The Brinell method is a common method used to measure the hardness of a metal. A machine is used to press a 10 mm hardened chrome steel ball with the same force as an equivalent mass of 3,000 kilograms into the metal being tested. The diameter of the resulting impression is used as a measure of the metal's hardness. The Brinell value, or number, is the ratio the mass of the object divided by the surface area of the indentation. Steel can be hardened by heating it to a very high temperature, then suddenly cooling it by putting it in water. However, it then becomes brittle. The cooled steel can then be tempered, toughened, by reheating it and allowing it to cool slowly. As the steel cools, it loses hardness and gains toughness. If the steel cools down slowly and completely, we say that it is annealed. Annealing is a process by which the properties of steel are enhanced to meet machinability requirements. Annealing is the process of heating the steel slightly above the critical temperature of steel, 723 degrees Celsius, and allowing it to cool down very slowly. Some of the advantages of annealing are: it softens the steel, it enhances and improves the machinability of steel, it increases the ductility of steel, it enhances the toughness of steel, and it improves the homogeneity in steel. Ductility is a solid material's ability to deform under tensile stress. This is often characterized by the material's ability to be stretched into a wire. Malleability, a similar property, is a material's ability to deform under compressive stress. This is often characterized by the material's ability to form a thin sheet by hammering or rolling. Elasticity is the ability of a body to resist a distorting influence or stress and to return to its original size and shape when the stress is removed. Solid objects will deform when forces are applied on them. If the material is elastic, the object will return to its initial shape and size when these forces are removed. The elastic limit of a solid is the point beyond which a deformed object cannot return to its original shape. The spring's molecules were pulled far enough apart that they slid past one another beyond the point at which the original molecular forces could return the spring to its original shape. If the applied force is great enough, the spring breaks apart. Stress is the ratio of the outside applied force, which tends to cause a distortion, to the area over which the force acts. Stress is the ratio of the applied force divided by the area over which the force acts. Stress is usually measured in newtons per square meter, which is called the Pascal after Blaise Pascal. In these two configurations, the weight of the brick is constant, but the stress on the table is greater for the brick standing on its end. The area is smaller, yielding a higher stress. Which exerts a greater stress on the ground? An elephant, a dog, a person, or an ant? The correct answer is C, the person. But it is a bit of a trick question because it occurs under special conditions. Consider an average elephant weighing 5 tons, or 44,482 newtons. The area of 1 foot is 450 square inches, which is equivalent to 0.290 square meters. If the weight of the elephant is distributed over all 4 feet, the total stress on the ground is over 38,000 newton per square meter, or around 5.6 psi. What is the stress on the ground from a 100-pound, 440 newton woman wearing stiletto heels? All her weight is on one heel. The area of the heel is 1/4 inch by 1/4 inch, or 4 times 10 to the minus 5 square meters. The total stress is 11 million newtons per square meter, or about 1600 psi. I wonder what the stress is if the elephant wore stiletto heels. There are 5 types of stress we will consider: tension, compression, shearing, torsion, and bending. Tension is 2 pulling opposing forces that stretch an object trying to pull it apart. For example, pulling on a rope or a car towing another car with a chain. The rope and the chain are in tension or are being subjected to a tensile load. The drawing is of a beam with 2,000 pounds of force pulling it apart from each end. Inside, molecules are pulling back, trying to stay together and keep from being ripped apart. 2 pushing opposing forces that squeeze an object together is trying to compress it. For example, standing on a soda can, squeezing a piece of wood and a vise. Both the can and the wood are in compression or are being subjected to a compressive load. Shearing occurs when there are 2 pushing or pulling forces acting close together but not directly opposing each other. A shearing load cuts or rips an object by sliding its molecules apart sideways. For example, pruning shears cutting through a branch, a paper cutter cutting through paper. The branch and paper are subjected to a shear loading. Torsion is created when a moment or turning force is applied to a structural member or piece of material, making it deflect at an angle or twist. A moment that causes twisting is called a twisting or torsional moment. Torsion produces shear stresses inside the material. A beam in torsion will fail in shear. The twisting action causes the molecules to be slid apart sideways. For example, a pole with a sign hanging off one side. Bending consists of both tension and compression stresses. It occurs when a force is placed on an object and this causes it to sag. An example of bending is caused by a person sitting on a board. The top section of the board is being pushed together in compression, while the bottom section of the board is being pulled apart in tension. Hooke's law is the ratio of the force applied to an object to its change in length, resulting in its being stretched or compressed by the applied force. It is constant as long as the elastic limit has not been reached. Mathematically, we write the applied force divided by the change in length is equal to the spring constant. Hooke's law only applies to the elastic region of a spring. If the applied force is too great, the elastic limit is reached and the spring will deform. It will undergo various types of deformation as the applied force increases until eventually the spring breaks. A force of 3 pounds stretches a spring 12 inches. What force is required to stretch the same spring 15 inches? This is a Hooke's law problem, where the force is the spring constant times the change in length. This is the same spring stretched to two different values. The spring constant is the same for both scenarios. We assume the elastic limit has not been reached. We can use proportional reasoning to find the unknown force since the spring constant is the same in both cases. Substituting the known quantities and solving for the unknown force gives a pull force of 3.75 pounds.